Right, I would like to give you an overview of our paper together with Naomi Nickerson about a new architecture for surface code quantum computers. And in this one, we explore how to take advantage of long-range connectivity between physical components to execute quantum computations much faster. And our starting point was the following. All the general purpose architectures for surface code quantum computers that had previously been described in the literature, they are all of the type where the cost of a quantum computation is determined by the number of qubits in the computation multiplied by the number of T-gates. And that's because they all correspond to some arrangement of logical qubits in which gates are executed sequentially, one T-gate after the other. So when you want to know how costly it is to run a quantum computation on such a device, all you need to do is count the qubits in the algorithm, count the T-gates, and then multiply the two numbers to get the space-time volume. And we call architectures like that baseline architectures because they have relatively simple hardware requirements and therefore provide a baseline for the cost of a quantum computation. Now, when I say simple hardware requirements, these baseline devices, they're still devices that are extremely difficult to build. But what I mean is the following. In a baseline architecture, the quantum computer can be thought of as an array of surface code patches where each patch is a logical qubit. And logical operations are possible between neighboring pairs of logical qubits, for example, by performing lattice surgery, which is essentially a way to implement logical two-qubit Pauli measurements between pairs of logical qubits. And there are various ways to implement such a 2D arrangement of logical qubits. The most commonly known one is to think of it as a big 2D array of physical qubits like superconducting qubits, where each logical qubit consists of a square grid of physical qubits. And of course, typically, each logical qubit will contain thousands of physical qubits in a practical scenario, not just 25 as drawn here. But another approach is the photonic approach, where the quantum computer is not an array of physical qubits, but instead, it's a network of photonic resource state generators. And each resource state generator produces copies of a few photon resource states repeatedly and comes with a fiber delay that is used as a temporary memory for a few thousand of these resource states. But in this network, you can think of each resource state generator as being associated with a logical qubit. But you should think of resource state generators as macroscopic, multi-chip sized devices, and the connections between them as macroscopic fiber optic links. So because connections between the different modules in a photonic quantum computer are implemented via macroscopic fiber optic links, you don't necessarily need to connect them up in a square grid like that. You could connect the modules in a network without any locality constraints. And in addition to that, photons routinely need to go through switches that select their destination. So we can use fiber links and switches to not only establish connections between faraway modules, but also have switchable connections. So the neighbors of each patch can not only be far away, but you can also have a much larger pool of potential neighbors available. So we came up with an architecture that looks roughly like this. You still have a network where each module is a logical qubit, but the connectivity graph is very different. Rather than being constrained to two qubit operations between nearest neighbors in a 2D grid, each logical qubit can participate in two qubit operations with qubits from a much larger collections of potential neighbors like this. One thing that was very important to us is that we didn't want to have an architecture that relies on all-to-all connectivity, because all-to-all connectivity implies having a very large photonic switch, which typically results in worse device performance. Instead, each module in this network is only connected to a number of modules that is logarithmic in the total number of logical qubits. And in practice, this results in a few dozen switch options in a network of thousands of logical qubits, which is a reasonable switch size for photonics. And our key result that I will explain to you is that such a network can be used to implement quantum computations with a cost function that is different than the circuit volume. And we call this cost function the active volume. Each logical qubit, each logical operation, such as a Toffoli gate, a multi-qubit Pauli measurements, or bigger operations like an adder operation, has a cost associated with it that we call its active volume. And the total cost of a computation is obtained by just summing up the active volumes of all operations. And importantly, the number of qubits does not appear in the cost function. So in many cases, the active volume can be orders of magnitude lower than the circuit volume, which means that these switchable non-local connections enable the quantum computer to finish quantum computations much more quickly. Here's another way to phrase it that is perhaps a bit more memorable. Quantum algorithm developers put a lot of effort into crafting delicious chips that are well-optimized quantum algorithms with low qubit counts and Toffoli counts. But whenever we take those algorithms and package them into a fault-tolerant quantum computation, we end up adding a lot of stuff that we don't really need. We add all this air that are operations that are used to make faraway logical qubits communicate with one another, or identity gates that are used to idle logical qubits that are currently not being used in logical operations. And we often end up in a situation where the vast majority of resources is spent on air rather than on chips. The active volume architecture allows us to use long-range connections to package our algorithms much more efficiently. We don't get rid of all of the air, but we end up with fault-tolerant quantum computations that are sort of equal parts chips and air, so that we can put all our delicious chips in a much smaller package. One thing to mention here is that we're comparing general-purpose architectures here. There exist special-purpose architectures in the literature that use local connectivity and can execute specific quantum computations more efficiently than the general-purpose architecture with local connections. Like, for example, the optimized factoring constructions by Gidney, Fowler, and Ekra. But what we discuss in the following outperforms both general-purpose and special-purpose architectures with 2D connectivity. And importantly, the architecture that we wanted to construct is a general-purpose architecture. So we don't want a different quantum computer for every computation. We just want one efficient general-purpose machine. Before we look at the active volume architecture, let me just briefly review how a baseline architecture works, in which we execute operations sequentially. So the types of architectures that do not require long-range connections. The very quick summary is that any Clifford plus T circuit, any quantum computation, can be converted into a sequence of multi-qubit Pauli measurements and multi-qubit pi rate rotations, basically a long sequence of generalized T-gates. By applying a circuit identity, every one of these generalized T-gates is replaced by the preparation of a magic state and a multi-qubit Pauli measurement. In a baseline architecture, a surface code quantum computer that executes these operations sequentially could, for example, look like this, where each one of these rectangular patches here is a logical qubit, and all logical qubits are just arranged in a line. This is an example of a 5-qubit quantum computer, and a 100-qubit quantum computer would be the same linear arrangement, but longer. In this example, the entire quantum computer consists of 2 long rows of logical qubits, and big Pauli measurements involving multiple qubits are executed sequentially, one after the other, using the bottom row to connect all qubits that participate in the measurement. Whenever an operation requires a magic state, we generate one in this additional part of the quantum computer called a distillation block, perform a multi-qubit Pauli measurement, and remove the magic state. And then we generate the next magic state, execute the next big Pauli measurement, and remove the magic state. And this is really the main process that repeats over and over again for the potentially billions of T-gates that we have to execute in the circuit until we finish the quantum computation. So that's how a baseline architecture works in a nutshell. You just execute multi-qubit Pauli measurements and magic state preparations sequentially until you're done with the quantum computation, which is why the relevant cost metric is the number of qubits, the footprint of the quantum computer, times the number of T-gates, which is the duration of the quantum computation. Now let's talk about the active volume architecture. In an active volume architecture, we use the switchable long-range connections to parallelize operations so that the quantum computer can execute a much larger number of operations at the same time. Let me describe in a bit more detail how this works. On a first glance, the active volume architecture looks very similar to the baseline architecture that we've seen previously. An active volume quantum computer consists of a number of qubit modules. In this example here in the top left, 24 qubit modules. Each qubit module can store a surface code patch, so a logical qubit, or it can be empty. And in this case, we label the qubit modules from 1 to 24, and we call the modules with an odd label memory modules, and the modules with an even label workspace modules. We'll draw them as 2 rows of modules to make them look somewhat similar to a baseline architecture, but it's important to note that modules are not associated with a position on a 2D grid. All that modules have is a label from 1 to, in this example, 24, but not a position on a grid. On the right-hand side, we will also draw 2 descriptions of the state of an active volume quantum computer, in this case consisting of 16 modules instead of 24. And there's a fine-grained one showing operations on physical qubits, and a coarse-grained one at the bottom. The set of available operations is shown on the left. Some operations are fast, meaning that they take 1 code cycle, while other operations are slow, meaning that they take decode cycles, so dozens of code cycles, just like a lattice surgery operation. The first operation is a fast operation that we call a quick swap. A quick swap swaps the contents of 2 qubit modules within 1 code cycle, but not any pair of qubit modules can participate in a quick swap, only pairs of qubit modules whose labels differ by a power of 2, which is how we get sort of this logarithmic number of connections. So for example, the contents of these 2 modules or of these 2 modules can be swapped, and multiple quick swaps acting on disjoint sets of qubit modules can be performed simultaneously. And we will use quick swaps as operations that let us quickly rearrange the memory. Quick swaps can also be used to swap qubits between memory modules and workspace modules, since these have a label difference of 1. And quick swaps are implemented via physical qubit swaps between pairs of modules. So you physically swap the locations of the logical qubits. While quick swaps rely on this kind of logarithmic long-range connectivity, the other operations rely on short-range connectivity. They can only be performed between modules that are in range, meaning that their module label difference must be below some number r, which we refer to as the range. This is a fixed number that will depend on the specific hardware implementation, but really a range of around 12 or so is more than sufficient. So for modules whose labels numbers differ by no more than 12, we can perform the following operations. First, we can perform lattice surgery operations between qubits stored in these modules, so we can perform logical XX and ZZ measurements. Now, the lattice surgery operations described here are slightly different than the typical lattice surgery operations found in the literature, because they are lattice surgery operations involving two edges located on the same side. To visualize what this means, what we need to be able to do is take the two patches in the two qubit modules that are in range, slide the two patches on top of one another, and then perform measurements involving physical qubits on the left side of both patches, implementing a lattice surgery operation, so a logical two-qubit poly measurement. In the paper, we use these hexagons to describe a collection of lattice surgery operations, and the notation here is based on the ZX calculus, but in the context of this talk, all you need to know is that these symbols, they describe lattice surgery operations. When we describe operations like this, we refer to each one of these hexagons as a logical block. So for example, these three logical blocks here, they are a way to describe lattice surgery operations involving three logical qubits, in this case, these lattice surgery operations. Logical block operations are slow operations, meaning that they take d code cycles to execute. And if you think of d as 30, then in the time it takes to execute a collection of logical block operations, you can perform 30 layers of quick swaps. And finally, the last operation is also a fast operation, meaning that it takes one code cycle, and that's a transversal Bell measurement. Two qubits stored in qubit modules that are in range can participate in a quick Bell measurement that measures the two-qubit poly operators XX and ZZ. In terms of physical operations, this corresponds to taking two surface code patches, sliding them on top of one another, and then performing physical Bell measurements between pairs of physical qubits. This is a destructive measurement. So for example, we can measure qubits Q5 and Q6, and then they're gone. Bell state preparations can also be done the same way. So a logical Bell state can be initialized in a pair of qubit modules that are in range within one code cycle. It's worth pointing out that these operations are not the same as logical transversal C0 gates. So we're still doing lattice surgery. Logical transversal C0 gates are not used in the paper, although they can, in principle, make things even faster. Okay, so our quantum computer is a network of qubit modules where we can perform long-range quick swaps and short-range lattice surgery operations. How do we use this to execute a quantum computation? Let's look at an example. In an active volume architecture, we no longer think of a quantum computation as a sequence of just generalized T-gates, but a more general sequence of operations from a set of supported operations. The set of supported operations includes T-gates, but may also include larger operations like quantum arithmetic operations and quantum Fourier transforms. Even magic state distillation in this context is a logical operation like any other. Each operation is described as a network of logical blocks. The more blocks an operation contains, the more costly it is. For example, operation 1, it has 2 input qubits and 2 output qubits and consists of 4 blocks. And as I mentioned, these blocks are really just a description of parallel lattice surgery operations. Don't worry about which specific operations these logical block networks correspond to. Just think of these 5 operations as some arbitrary sequence of a 4-block operation, a 2-block operation, a 6-block operation, a 2-block operation, and another 3-block operation. Think of the number of logical blocks, or hexagons, an operation contains as a measure of how expensive it is. So 6 logical blocks means that 6 logical qubits will be busy doing lattice surgery operations for 1 logical cycle to execute this operation. Just as in a baseline architecture, we structure our quantum computation into logical cycles, so sets of decode cycles, which is how long it takes to execute a logical block operation. But in contrast to the baseline architecture, we won't just execute 1 logical operation in each cycle, but as many as we can. In our workspace, we have the capacity to execute 6 logical block operations at the same time, so we will attempt to do just that. First, we load qubits 2, 5, 3, and 6 into the workspace via quick swaps. These are the qubits that participate in operations 1 and 2. And then we simply copy the logical block networks of operations 1 and 2 into the workspace register. While we're executing operations 1 and 2 in the workspace, we have a lot of time to execute quick swaps to rearrange our memory in preparation for the next logical cycle. We move qubits Q1 to memory location 1, and qubit 4 to memory location 6. The reason why we want to do that is that once operations 1 and 2 are finished, we just need to do one layer of swaps between memory and a workspace, and we're ready to execute the next set of operations. In this case, we only have the capacity to execute one operation, since operation 3 is particularly costly. But again, we copy the logical block network of operation 3 into the workspace, and are again free to perform some quick swaps. We perform one layer of quick swaps and a second layer of quick swaps, and once the second logical cycle is completed, we swap qubits between memory and workspace, and are ready to execute operations 4 and 5. And this is basically the process that repeats over and over again. We use the workspace to execute as many operations in parallel as we can, and in the meantime, we rearrange the memory to prepare for the next set of operations. One important thing to mention is that the operations that you execute in parallel, they don't need to commute, and they don't need to act on different sets of qubits. For example, here we have two operations in an 8-qubit circuit, but both operations use qubit 5. One is a 3-qubit measurement on qubits 1, 5, and 8 with a cost of 5 blocks, and the other one is a 2-qubit measurement on qubits 5 and 7 with a cost of 2 blocks. So let's say we have this bigger active volume quantum computer with the 8 qubits stored in memory. The combined costs of these two operations is 7 blocks, so it would comfortably fit into the workspace, but both operations have qubit 5 as an input. To execute both operations at the same time, we can use what we call bridge qubits. We essentially have the situation where we want to execute operations A and B simultaneously, but both access the same qubit. What we would like to be able to do is basically bend the qubit line to be able to execute operations A and B concurrently. And this line bending is really implemented via teleportation, so Bell state preparation and Bell measurement. To execute operations A and B at the same time, we prepare a Bell state, where we refer to the 2 qubits of the Bell state as B and B tilde. One of the qubits is used instead of the shared qubit in operation B, while the other one is referred to as a bridge qubit. After the operations are, this bridge qubit is stored in memory. After the operations are completed, the bridge qubit that was stored in memory is destroyed in a Bell measurement with the output qubit of operation A, completing this protocol. In our example, the following happens. We load qubits 1, 5, and 8 into 1, 5, 8, and 7 into the workspace, and at the same time, we initialize a Bell pair, where one half is in the workspace and the other half is a bridge qubit in the memory. We write the logical block networks of both operations into the workspace, and note that the protocol tells us that the bridge qubit B1 tilde needs to participate in a Bell measurement with the output of operation 1 at the end of the logical cycle. So while the logical block operations are being executed, we need to move B1 tilde, the bridge qubit, to memory location 3 in preparation for the next step. After the completion of the logical block operations, we can destroy the 2 qubits with a Bell measurement, completing this bridge qubit protocol. This was a bit of a fast overview, but it's described in more detail in the paper, and I'll summarize it in a bit. Now, I haven't spent a lot of time describing how one would implement such an active volume quantum computer. The non-local connections required to achieve this performance gain are primarily motivated by photonics, as they might be difficult to implement with other qubit platforms. In the paper, we present a very concrete implementation with photonic components, but explaining this implementation in detail would require more time. But just to give you a very rough idea, mainly to convince you that we have a very concrete hardware implementation in mind when describing this architecture, the implementation relies on the interleaving architecture described in a previous paper. In this architecture, the quantum computer consists of a network of interleaving modules. Each interleaving module consists of a photonic resource state generator, repeatedly producing identical copies of few photon entangled states, some photonic fiber delay lines, some switches, and single photon detectors. In terms of physical stuff, we're talking about integrated silicon photonics here. So don't think of an optical table with laser beams and lenses and bulk components. The devices look like standard computer chips, lots of chips interconnected by fiber cables, just like in a big data center. In a baseline architecture, these interleaving modules are arranged in a 2D grid. The active volume modules that we describe in the paper are very similar. Their main difference lies in an increased number of switch options that are used to switch between a logarithmic number of different neighbors. So we still have a network of interleaving modules, but the increased number of switch options allows each interleaving module to route its photons to a greater number of receiving modules. And that way, the switch from baseline architecture to active volume architecture implies only minor hardware changes in a photonic implementation. Now, this slide summarizes the differences between the baseline architecture and active volume architecture. So if you're a bit jet-lagged or got distracted with something else or you're lost, now is a good time to pay attention. pay attention to understand the key differences between these general purpose architectures. A baseline architecture, which is this 2D local connectivity thing, consists of n logical qubits, where roughly half are used for memory, and the other half is workspace to execute logical operations. Each logical qubit here is drawn as a square, but really corresponds to potentially thousands of physical qubits. A few logical qubits are reserved for magic state distillation, but this is only a small fraction in a device with thousands of logical qubits as required for many useful quantum computations. A baseline architecture executes gates entirely sequentially. Magic states are produced in this distillation block and then consumed to execute logical operations, occupying the entire workspace to connect the produced magic state to whichever memory qubits participate in the logical operations. So if you have n logical qubits, then you have roughly n half logical qubits of memory, so you can execute quantum computations that require this many qubits. But the speed is always 1 T-gate per logical cycle, or 1 Toffoli gate every 4 logical cycles. Here, 1 logical cycle is d code cycles, where d is the code distance, think of it as roughly 30. And the length of a code cycle can range from 1 microsecond for superconducting qubits to 1 millisecond for ion traps. And for the photonic qubits we have in mind, it's likely to be around 10 microseconds. That is to say, if you know how many Toffoli gates you need to execute, you can also compute how many minutes, hours, or days it takes to finish the quantum computation. In an active volume architecture, the picture is a bit different. We still have half the qubits used for memory and half as workspace, although now distillation is also done in the workspace. But rather than executing operations sequentially, we use the long-range connections to parallelize operations. To quantify how many operations we can execute in parallel, we say that with n half workspace qubits, we can execute n half logical blocks per logical cycle. Different operations have different costs, and the number of logical blocks is a measure of how costly an operation is. So logical blocks are basically the currency that we pay for logical operations. For example, the cost of a Toffoli gate and an adder is roughly 60 blocks. The workspace is used to execute as many operations in parallel as possible, and the primary purpose of these long-range connections between logical qubits is to quickly rearrange the memory between logical cycles, since different operations access different qubits that are stored in different memory locations. So the main difference between the baseline and active volume architecture is that whenever we add 2 logical qubits to an active volume quantum computer, we increase the memory and we also increase the speed, whereas in a baseline architecture, the speed remains constant. It's worth pointing out that you can't run quantum computations arbitrarily fast, throwing more hardware at them. There's a speed limit related to the depth of the algorithm and the so-called reaction time, which is explained in more detail in the paper, although in many cases you don't need to worry too much about this reaction limit. With active volume in mind, we should think of our algorithms not in terms of small gates like C-naughts and Hadamards and Toffolis, but instead in terms of big subroutines like adders, comparators, and table lookups. If we want to perform resource estimates for these two different architectures, the steps are very similar, but there are some small differences. For a baseline architecture, we need to count the number of Toffoli gates, but for an active volume architecture, we need to sum up the active volumes of all subroutines. This is similar to counting Toffoli gates, but there can be some differences since the ratio between active volume and Toffoli count differs from subroutine to subroutine. The reason for that is that active volume also keeps track of the cost of Clifford gates in addition to the cost of magic states, because Clifford gates cannot be assumed to be free when you're parallelizing operations like this. Generally speaking, arithmetic subroutines like adders, controlled adders, comparators, and so on, they have a very favorable ratio of roughly 60 blocks per Toffoli gate. On the other hand, lookup tables, or QROM lookups as they're called, can be much more costly in terms of active volume, since their active volume scales with the size of the bit strings that are loaded into the quantum computer, whereas the Toffoli count does not. So if you're loading 1 million numbers into the quantum computer using a lookup table, then it takes 1 million Toffoli gates, whether these are 32-bit numbers or 2048-bit numbers. But for the active volume, the size of these numbers makes a big difference. One of the main motivations behind describing general purpose architectures with simple cost functions is that you don't have to be an expert in quantum error correction to perform a fault-tolerant resource estimate for your quantum computation. There's a second paper that uses the quantum algorithm for breaking elliptic curve keys as a case study for how to optimize the algorithm and perform a simple resource estimate in the active volume architecture. The steps are very simple. I'm going to describe it, I'm not going to describe it in great detail, but just to give you a rough overview. We break down the algorithm into modular arithmetic operations, and then these operations to basic non-modular arithmetic operations and QROM lookups, which allows us to determine their Toffoli counts and active volumes. The only input to the resource estimate, really, is this table from the previous slide. There are also 3 simple tricks described in the paper that are used to reduce the Toffoli count by up to a factor of 5 compared to the previous state of the art, which also reduces the active volume. And putting all these things together, we get an active volume estimate to break 256-bit elliptic curve keys. Because the qubit count and active volume are enough to estimate concrete device sizes and runtimes, the paper explains how to straightforwardly use these numbers to compile a big table like this, showing device footprints and runtimes for different qubit platforms and different variations of the algorithm. And you can expect this table more carefully by reading the paper, but the main result here is that in this case, the active volume architecture can execute the computation up to 700 times faster than the baseline architecture. And that's on top of this architecture-independent factor of 5 improvement to the algorithm. So long-range connections can be a very useful thing, even in the context of surface codes. So if you want to read more about this, you can read these 2 papers at the top. The first one is the paper about the active volume architecture together with Naomi Nickerson. And then there's also this related paper about breaking elliptic curve keys. And if you want to learn more about this modular photonic interleaving architecture that I mentioned, but didn't go too much into detail, there's also this paper about interleaving. And with that, we've reached the end of the talk.
Thank you, Daniel. Floor is open for questions. Let's see, we got one over there. Close to the microphones.
Thank you. It's an excellent talk. So this is not the first extremely parallel quantum computing architecture you've proposed. Your Game of Surface Codes paper has a very different but also very parallel architecture in it that relies on mass producing T-states simultaneously and applying them. How does this compare to that one in terms of strengths and weaknesses? And why would you use one over the other?
Yeah, so in the, let me find the relevant slide, actually. Okay, so basically, when you do these linear space-time trade-offs, as described, for example, in this Game of Surface Codes paper, then you don't change the space-time volume. You sort of do a trade-off where you use twice as much footprint to execute the computation twice as fast. So the overall space-time volume remains constant. Space-time volume meaning number of qubits multiplied by number of time steps that you need to execute the quantum computation. Here it's different because the active volume architecture achieves a smaller space-time volume. So we actually reduce the size of the quantum computation. We can still do linear space-time trade-offs on top. So there's always this flexibility of using twice as much hardware to execute the computation twice as fast. This is not what the speed up is about. This is about using the components that you have more efficiently. Sort of you're extracting more computational value from the same amount of hardware.
Thank you.
Question there?
Hi. So how much progress has actually been made towards these resource state generating blocks in the new architecture with the fancy switches?
Oh, so in this architecture, this architecture is sort of, it doesn't tackle the problem of implementing resource state generators. We are assuming, this architecture is about what happens on the levels above the resource state generator.
Yeah, sorry. So I mean, in this whole big yellow square on the right, like how much of this exists?
Oh, how much of it exists?
Yes.
Well, resource state generators do not exist in the form that is useful for a surface code quantum computation.
Okay, cool. Thanks.
But the elementary hardware components that go into them, they do exist. If you look at what kind of stuff does this actually correspond to, that the physical components that go into a photonic quantum computer, they're single photon sources, they're switches, they're detectors, single photon detectors, and interconnects between photonic chips. On all levels, they're the same hardware components. If you want to do surface code quantum computation with them, the main challenge is that every single component can be lossy. So the main challenge if you want to construct a quantum computer that can actually perform surface code quantum computation is that all these components need to be integrated in the same chip, and they all need to have low loss rates. Before that, you cannot build a surface code quantum computer because you will not be able to execute surface codes below threshold.
Thank you.
So there's a question right there, table 19.
Thank you for the talk. So it's about the resource state generators. I just, if you claim that it's a significant improvement in resource costs with the active volume, with the long distance connections, but don't look at the contents of the RSG. Maybe the resource overhead is very high and it's just a hidden cost inside. Do you have any evidence or intuition suggesting that the RSGs actually provide a beneficial overall cost compared to other methods of constructing fault-tolerant states?
So no matter what kind of, in this kind of photonic fusion-based quantum computing architecture, the elementary building blocks are these resource state generators that produce, photonic resource states. The cost of a quantum computation is essentially, when we talk about space-time volume, the cost of the computation is really how many resource states do we need to generate to finish the computation. All that the hardware does is produce photons and measure photons. If we want to know how long it takes to finish the computation or how much hardware do we need to finish the computation, it's about how many resource states, how many photons do we need to generate. The difference between active volume and baseline architecture, this resource saving, is that to execute the same quantum computation, we just, strictly speaking, using the exact same resource state generator, the exact same resource state, we need to generate fewer of them to finish the same quantum computation. So the resource state generator is, in both cases, can be the same. There is sort of, okay, so maybe one thing to mention is this picture is not a chip footprint or anything like that. This is a conceptual picture of what the computer looks like. The vast majority of the complexity in building a photonic quantum computer is inside this resource state generation box. Because resource state, there's no elementary physical component that just outputs a many photon entangled state. So this component that we need is, the resource state generator is something that we want to produce a few photon entangled state. It's a constant size state, but it's a state containing dozens of photons. That's sort of the order of magnitude. But the elementary hardware components are things that produce single photons, and out of single photons we can build bigger entangled states, and out of a few photon states we can build even bigger entangled states. But this takes multiple hardware components. This is not, even though this looks like a small box in this diagram, really if you were to draw these things to scale, this would be much bigger than everything else.
One last question over here.
Thank you, Daniel, for a wonderful talk, as always. We saw yesterday with trapped ions and today with trapped neutral atoms that early fault-tolerant quantum computers are making great use of this 832 code, the code that Earl Campbell's dubbed the smallest interesting color code. It's got this feature that it has a transversal non-Clifford, and that can be nice for certain algorithms where you can just avoid distillation altogether. So it's a 3D color code. It can do lattice surgery if you like that. It can do transversal gates if you like that. What do you think the prospects are for thinking about these 3D codes in an active volume architecture? Is it something that you think could be viable, like for early fault-tolerant quantum computers or even large-scale ones, or is this active volume architecture really finely tuned for 2D topological codes with lattice surgery?
Well, at the end of the day, any kind of alternative prescription to magic state distillation that executes non-Clifford gates in a different way can be viewed as just sort of a different. You can sort of plug it in instead of magic state distillation into your architecture. And the question would always be, is it actually cheaper than magic state distillation? Because with magic state distillation, there are a lot of tricks we can play to shrink the protocol in certain places. And so far, I have not, so far I have not seen anything that actually would outperform magic state distillation in a practical setting. Although there can be more exploration done in this direction, but yeah, if you have a different way of doing non-Clifford gates, that's basically like saying I have a better distillation protocol that doesn't look like a standard distillation protocol that you typically think of.
I guess maybe what I'm asking is, can we just take these blocks with surface codes and put a different code in instead? Is the active volume architecture so closely tied to the surface code that it has to be with that, or could we put a different code in instead?
Well, it is closely tied to, I guess it is closely tied to 2D topological codes because you sort of rely on this description of, logical operations in terms of logical blocks, these kind of space-time volume chunks that you get in a surface code type architecture. There are possibly other codes that could also, if you have a ZX diagram description of a logical operation, it's very simple with surface codes. You just take that and translate it into logical block network, into sort of a surface code prescription, how to execute that. I'm not sure how well this would apply to other codes. You can use other codes in conjunction with this. A question that comes up a lot, well, what about LDPC codes? You have long-range connections. These are not mutually exclusive things. You can sort of augment this by using LDPC codes for memory, or maybe a different code for distillation elsewhere. But yeah, so the basic description here, I think, does rely on surface codes.
Okay. Thanks a lot.
Let's thank Daniel and all the speakers of the morning. And we now break for lunch, and we reconvene at 1:30. Enjoy the lunch.